A2 Maths, Implicit Differentiation. Okay, so what we're going to look at is we're going to look at implicit functions and explicit functions. Now, most of the functions you've come across so far in maths have been what we call explicit functions. They are functions that you can write in the form y equals some function of x. So for example, it could be a quadratic function, y equals x squared plus 2x plus 3, or it could be a straightforward linear function, like y equals 3x plus 2, or it could be something like y equals sine x. Right, so if you could ever write it as y equals just some function of x, so you only have the x variables on this side, then it is called an explicit function. So grab your notebooks, just make sure you write down so you've got a clear definition of what an explicit function is. So an implicit function is something that's not an explicit function. So an implicit function is something that is not written in that form. So I'll give you an example of that, or an example that you might have seen already, is a circle equation written as x squared plus y squared equals 1. Is an example of an implicit function. Here's another example, x cubed plus xy equals 5. And so that's quite a neat form for the equation, but in that form it is not an explicit function. And that causes us some problems if I asked you to differentiate it, because all the functions you've differentiated so far have either been y equals some function of x, or we have actually looked at the other way around, x is some function of y. Okay, but we certainly haven't looked at being able to differentiate something in this form. Now, if I asked you to differentiate it, you could still do this, because what you could do is you could rearrange it and write it as an explicit function. So if I wanted to make it explicitly to do with x, in other words, put all the x's on one side, I could rearrange it by taking away the x cubed from both sides and then divided by x. So there we go. I can change from an explicit function, an implicit function to an explicit function by just rearranging it. Now the problem is you can't always do that. In fact, an example there is an example of an implicit function that you cannot rearrange to make y the subject. If you don't believe me, you can certainly try, see if you can rearrange it. Doesn't matter how hard you try, you will not be able to get it as just y equals. Okay, so pause there, make sure you got what you need in your notebooks. Okay, so like I said, being able to differentiate an explicit function is all you have done so far. But if we had a situation like that function we just looked at, where we couldn't write it as y equals, then how do we go about finding the gradient function? So let's give an example. If I want to work out the gradient function, changing y over the change in x, for the equation 3x plus y squared equals 2y minus 5. Now I could actually rearrange this equation to make it an explicit function, but this time I could make it x equals some function of y. But I don't want to do that. I want to have a look at how to differentiate it as an implicit. So the first thing I'm going to do is differentiate everything with respect to x. So I'm going to go through the function and just look at differentiating each part. Now that's what we usually do. We look at differentiating each part separately and consider what is the gradient function of each bit. Now I'm going to do the same with this. So I'm going to start with the differentiate the 3x, differentiate the y squared, differentiate the 2y, and differentiating the 5. Okay, so I'm just considering differentiating each part to see what happens. Now the first part, so the differentiating this bit, isn't too bad. It's just, can you find the gradient of the function 3x? In terms of x, yes, we could do that. It's just going to be 3. So this part just here is fairly straightforward. So if I differentiated it, we could certainly start off by saying the first part is just 3. Now what we need to do is differentiate each section of this individually. So now I'm going to move on to this part and consider what happens if I differentiate y squared. Now this is the one that's a bit more awkward. So what we're going to look at is differentiating it using chain rule. If that was an x instead of a y, of course it would be quite straightforward. We could just write it as 2y. All right, it wouldn't be a problem at all. If it was an x, it would be 2x. But because it's a y, and because you're differentiating in terms of x, you can't just do it straightforward. We have to make sure that we are differentiating in terms of y for y squared. That was easy because these two were the same variables. This was more tricky because these two are different variables. So what we're going to do is we're going to consider doing it using the chain rule. And the way we're going to do it is changing that dx into a dy. If I had dy on the bottom, it would work out fine. Now I can just do a little bit of cheating. I can change d over dx using the chain rule and put in a dy over dx on the front. Just consider what happens here. That dy and that dy will cancel out and you'll end up with d over dx. Okay, so it's not technically true, but that's basically how you could look at it. If these two cancel out, you've got d over dx, which is what we got there. So all I'm doing is separating it out and manipulating it so that I end up with d over dy here. And now these two parts are the same, I can now differentiate it as we would do normally. How do I differentiate y squared in terms of y? It would go to just 2y. The problem is, why is it different? I've got this extra dy over dx put at the front. So this dy over dx is put at the front. So what I can do is I can just write the differentiation of y squared in terms of dx is 2y dy over dx. Now this is always what happens. If you're differentiating one of the y functions, so something like y squared or 2y, you're differentiating a y function in terms of x, all you do is differentiate as you would do normally. So y squared goes to 2y, but because it's y, you put the dy over dx in there as well. Okay, and that would work for any function. If you're differentiating in terms of x, but it's a y value differentiating, you differentiate it as normal. So y squared goes to 2y, and you must remember to chuck in this dy over dx on the front of it. Okay, let's look at that example again though, or a slightly different example. So that goes to dy over dx 2y. Right, I've got an equal sign, so I'll put my equal sign in, and now I'm going to consider this part. What's the differentiation of 2y? But just to see it again, just make sure we're happy. So d over dx, we can separate out using chain rules. So these dy's can cancel and you've still got the d over dx, which I started with. What's the differentiation of 2y in terms of y? The answer is just 2. And because it's y function, I've still got that dy over dx. So you do not need to do the chain rule every time. As long as you have got some awareness of that's what's happening, you can literally just say the differentiation of 2y goes to 2, but because it's y, dy over dx. Right, what about the differentiation of 5? Now, as we know, if we try to differentiate a number, it has no gradient because it's a straight line. It has a gradient of 0, so therefore we can just ignore that part completely. We don't even go to plot plus 0, it will just disappear. Okay, so there's my gradient function. It's a bit messy though, and ideally we want dy over dx on its own at the front. So I can do a bit of rearranging now. I can certainly put everything with dy on the same side. Right, so if I do that first of all, so I'll put everything with dy on the same side, and then I can factorise out the dy over dx. So everything with dy over dx on one side, leave the number 3 on that side, and then I can factorise. So just make sure you're happy where that comes from. Taking that over, it's minus, factorise out 2 minus 2y. To get my dy over dx though, what do I do at the end? Divide by 2 minus 2y. So there we go, there's my original function, and there's my gradient function just there. Noticing that it ends up with y values in, there's nothing wrong with that. And in fact, for a lot of the implicit functions, you'll end up with x's and y's in the gradient function. Okay, so just pause there, make sure you got down what you need in your notebook. Right, and still sticking with your notebook, what I'd like you to do, please, is just get this exam question down and just have a go at differentiating it yourself first. You might not want to put it in your notebook, but just have a go at differentiating it, and then we'll have a look through the question. Okay, so just play it when you're ready. Okay, so let's see how far you got then. So the first thing I want to do is differentiate this function. So I'm going to differentiate both sides. Now it's a bit more technical than the previous one, because we're going to use some differentiation skills that we've just learned. So differentiation using chain rule and differentiation using product rule. So let's have a look at this side first of all. So I'm differentiating 4y e to the 2x. Now, thinking that y and e to the 2x are different functions would mean that I've got 4y times by e to the 2x. So on this side just here, I'm going to be using the product rule. Okay, so let's use the product rule on that. And just remembering how the product rule works. It means you differentiate part of it, leave the other function alone, and then differentiate the other function and leave the first function alone. So what I'm going to do is just consider my two functions separately. I've got 4y as one of my functions, and I've got e to the 2x as my other function. So I'm differentiating uv. Right, differentiation of 4y. How do I differentiate 4y? Well, because I'm differentiating in terms of x, I need to differentiate it as I would do normally. So what does 4x go to? Just the number 4. But because it's y and not x, I need to put on the extra dy over dx. Okay, so I need to make sure that dy over dx function stays there. What about this one? Well, because it's x and I'm differentiating in terms of x, this one's straightforward, but don't forget it's 2x, so it'd be 2e to 2x. Okay, so I've differentiated them both and I've got the original function. So what I can do now is I can do my product rule. So it'd be that times that plus that times that. So let me put those together. Okay, so differentiate the first function. 4y goes to 4y over dy over dx. Leave that function alone. Then do the other function. So this time I'm differentiating the e to 2x, which is why we get the extra 2 to make 8. 2 times 4 is 8. And the y value is still there. Okay, right, now let's consider this side. Now this side is a function within another function. X plus y is the straightforward function on the inside. To the power 3 is the outside function. So because it's a function within a function, I should be thinking about the chain rule. Okay, so let's consider the inside function first of all. X plus y. So the x plus y function, if I differentiated that, I'd do them both separately. The x function will just go to number 1. Y on its own will also go down to 1, but because it's y and I'm differentiating in terms of x, I need to make sure I put on a dy over dx in there. So I'll get one lot of dy over dx. So that would differentiate to 1, that would differentiate to 1. Because it's y, I've got to make sure I always have this dy over dx in there. Okay, and for the keen people amongst you that are spotted, that's what you usually do. Whenever you differentiate in the past, think about your year 1 work when you first learnt it, notice that you had y equals equations, and when you differentiate them, they went to dy over dx, and that's the reason why. Okay, so that bit just there just reinforces what you've seen previously. The differentiation of y is dy over dx. Okay, so I've got my chain rule. I haven't quite finished it, have I? The differentiation of the inside function is that. So I need to put that down first of all. Then I differentiate the outside function. So to me, that would go to 3 lots of the inside function squared. So there we go, 3 lots of the inside function squared. Right, so that looks like quite a mess. So let me just neaten it up slightly. Just check you're happy. That times 1 is that. That times dy over dx is that. And what am I being asked to work out? Find the equation of the tangent of the curve at the point 0, 2. So I just dived straight in there and started doing differentiation. But clearly I needed to differentiate it because I need the gradient for the equation of the tangent. Okay, now it's given me a point. Notice that it gives me a full coordinate. So I got the x value and the y value. It's highly unlikely that I expect you to work out the y value, all right, because it's going to be a case of trying to work out the y value if x equals 0. Might not be that straightforward. Okay, so you can work out the y value. Sometimes it might be difficult, sometimes you might do it yourself. So they're giving you that point just there. So I've got an x and a y value. What I need is a gradient, and then I should be able to work out my equation of my tangent. Now I could just stick them into here straight away, or I could rearrange it and work out the gradient function dy over dx. It's totally up to you. In this question, they're not expecting you to work out the gradient function. They don't want you to work out dy over dx, but sometimes it's just helpful getting that. So let me just see if I could just rearrange this. So I'm going to take this function here, and put it on this side. So I've got all my dy over dx's. This function here that's not attached to a dy over dx, I'm going to take to that side. So I'm rearranging it. So I've got all my dy's on one side, all my functions without dy over dx on that side, and then I can just pull those both out and divide. So there we go. I've got a gradient function just there. That's going to make my life a little bit easier because now I need to just put these values in. Okay, it's still not straightforward. It's still a bit messy, but I think I can just about manage it. Okay, so there's my gradient function. So at the point 0, 2, so x is going to be 0, y is going to be 2. So let me just substitute those numbers in. There you go. And I'll do the number crunching for you. I put all those numbers in my calculator. Out comes the lovely number, a half. So now I've got the gradient at the point 0, 2. And I want the equation of the tangent there, so it's going to be y equals mx plus c, or y minus y1 equals m lots of x minus x1. So I can put it in that form if I want to. It's totally up to you. This one's the easiest because you don't have the c value. So therefore, once I've got that, I can see it's going to be half x plus an extra 2, or I can write it in this form, which is going to be just a case of doubling everything up. They will ask you for it in a certain form in an exam. But if they don't, you can use whatever form you like. So that would be more than acceptable. Okay, just pause, make sure you got down what you need for your notebook. So what I'd like you to do then, please, is I'd like you to have a go at finding the stationary points for that implicit function just there. So I'm going to pause. I want you to pause the presentation, the lesson, and have a go at differentiating it yourself. Okay, so don't just play it through. I want you to see if you can differentiate it yourself first of all. Okay, so let's see how far you got with your differentiation. So y squared. Well, if it was x squared, that would go to 2x. But because it's y squared, it's going to go to 2y dy over dx. X cubed, I could differentiate that. It just goes to 3x squared, no problem. And minus 2x squared will just go to minus 4x. So it's only this side here that's got this extra little bit. Okay, I can get my gradient function then, can't I? I can just divide by 2y. There we go. And from there, I asked you to work out the stationary points. So what does find the stationary points mean? It means when is the gradient function equal to 0? And that's actually quite nice, because if this is equal to 0, it means my numerator has got to be equal to 0. And if my numerator equals to 0, I can actually just work it out fairly straightforward from there, because it's just x equals 0 or x equals 4/3. Absolutely perfect. Okay, so I've got that, and yes, I could actually go back and I can work out my y values at that point. But what I'd like you to do is see if you can investigate those 2 points. Okay, see if you can spot any concerns with those 2 x values. So pause it there. Okay, I'll give you a hint if you need an extra hint. Okay, so don't just substitute them back into the original equation. Try to substitute those back into the gradient function as well. Okay, so pause again, have a go at that. Okay, so maybe if you'd substituted into the first equation, you would have said, I know what I could do. If I put x equals 0 in there, I can spot that when x equals 0, y is just going to equal 0 as well. Perfect. All right, clearly it has a stationary point at 0, 0. But the problem is this. If you look at the coordinate y equaling 0 and you go back to the gradient function, hopefully you can see a bit of a problem here. When x equals 0 and y equals 0, I end up with 0 divided by 0. Now that is undefined. When you try substituting it back into there, it is undefined because you cannot divide by 0. So although the maths is telling us there's a stationary point at 0, x equals 0, in fact for this function just here, there is not a stationary point at 0. So implicit differentiation, although it's fairly straightforward to find the differentiation of it, and I expect all of you to make sure you can do that in an exam, investigating stationary points is something that can always be a bit more tricky. So you must investigate the stationary points whenever you do implicit differentiation. So it clearly doesn't have a stationary point at x equals 0. Okay, the algebra was lying to you there. What about 4/3 then? Because surely 4/3 will work, because I'm sure that'll get a value. So let's just try it. So we can stick x equals 4/3 back in here. And I want to work out my y value. So I'll stick 4/3 back in. And if I do that, I do 4/3 cubed minus 2 lots of 4/3 squared. They end up with minus 32 over 27. But the problem with minus 32 over 27 is there's no real solutions. You can't square root that negative with and get a real solution. It's not possible. So therefore, this value as well is undefined. Undefined for a different reason. This one failed in the original function to find a y value. The other one failed in the differentiation equation, the gradient function, but both of them are undefined for different reasons. So that means although we used the differentiation function and got 0 equaling these two values, in reality, there is no stationary points at all for this function. This function does not have any gradient function. In fact, it looks something like this. If you drew it out, it would look like this sort of function. So it sort of goes up like that, and then it goes down like that. Okay, it looks like that. It has no stationary points at all. Okay, so let's have a quick exam question on this, and then I can get you on with some work. So again, what I would like you to do, please, is we're going to look at finding the stationary points on for this implicit function just here. I do want you to actually work out the gradient function of it yourself. Okay, because you'll need to do that for the stationary points. So I do want you to try differentiating it and then checking your answer first of all. Okay, so write it down, have a go yourself, pause there, and then we'll have a go. Okay, so the implicit differentiation. So I start with 9x squared, that's okay, 18x. This one, 6xy, if you didn't notice, is the product rule. So we do need to use the product rule here. So just make sure you're happy with where this comes from. Ignore the minus 6. I can just take that outside the differentiation, so that bit's okay. And then I could differentiate the x, which goes to 1. I leave the y alone, hence the y. Then I leave the x alone, and then I differentiate the y. Differentiating y goes to 1, but I put the dy over dx in. So just check. xy goes to that function just there. What about this one? Well, this one's a bit easier. What does 4x squared go to? It would go to 8x. So 4y squared would go to 8y. But because it's y, I keep that dy over dx in there. What does 3 go to? 0. All right, so well done if you managed to get that gradient function just there. We can neaten it up. All right, so a bit of expansion there. Put these dy over dx's, keep them together. We could take them to that side. But then once we've done that, we can factorize out the dy over dx. That's what we need to do every time. We're going to get 8y minus 6x, and then we could divide by 8y minus 6x and end up with our gradient function. So there we go. Lovely. I need to make sure that because it's implicit, when I got my stationary points, I must check it in there. Okay, this bit of work here is your standard work for pretty much a grade C, I would say, something like that. Checking your stationary points is talking towards the A's and A star work. So you must remember to do that. But let's do the first bit. Stationary point means the gradient function equals 0. The only way this is going to equal 0 is if the numerator equals 0. So the only way the numerator is going to equal 0 is if 6y minus 18x. And very interestingly, the the stationary points have come out as y equals 3x. So they've come out as an equation of a line, right? Which is something you wouldn't normally see. Normally you've got just a single x value. But that's not where it's finished. Now we know that the stationary points are when y equals 3x. What we can do with that is substitute it back into the original function to find where the stationary points are. So that's what I'm going to do now. Because I know that my stationary points are when y equals 3x, I can substitute them back in. That's what it's saying here. I can substitute my y equals 3x, okay, because on that line is where the stationary points are, back into this function to find out where they cross. So I can do that. I can stick in the 3x into the y. I can stick the 3x in for that y. And out comes this equation. A little bit of simplifying. I get a quadratic. All right, nice easy quadratic because there's no single x values. And I get this, 27x squared equals 3. What does that tell me then? X is plus or minus a third. Okay, because 3 over 27 is a ninth. So x equals plus or minus a third. My two stationary values are plus or minus a third. All right, that bit of work you've just done to get to there is, like I said, that is your C, maybe B grade work. This bit is the bit that's important. You must make sure that you get used to checking this function just here, this value just here, to see whether it's clearly defined in both the original equation and in the gradient function. So that's what we're going to do now. So we've got the two stationary points. When x equals a third, we can put it back into this equation. It's a little bit easier than that one. So when x equals plus or minus a third, y equals plus or minus 1, which is where you get these two coordinates. Let's just make sure they work. So they verify the station points in both the gradient function and the original. So certainly in the gradient function, in here, if I substitute both x's and y's in, it comes out to be 0. Absolutely perfect. We're not dividing by 0 because that's what happened last time. Okay, so this bit's not 0, but the numerator is. Okay, and that's the key thing. You're looking to see whether this comes out as 0 because that's the only time it won't be defined. But it doesn't, so therefore, big tick, it works fine. Also, what about this one? If I substitute that in, yes, that seems to work as well. So big tick, it is clearly defined for the gradient function. So therefore, the stationary points are also defined in this case. If you substitute back in the original, you'd also see that they're defined for y as well. So what I'd like to do, please, is have a go at these two exercises here. Some of it's just practicing implicit differentiation. Some of it's the more technical stuff where you're doing things like equations of tangents, equations of normal, stationary points, but also making sure you can use some of those other differentiation skills. Okay, I would strongly advise you have a go at nearly all of these exercises here. All right, these questions when they come up in your exam are worth big marks, and they are fairly straightforward once you know how to do implicit differentiation. Okay, so make sure you spend plenty of time practicing them.